Where did we stop? Where did we stop? We were doing ANN implementation. Hello.
Yes, ma'am, we are doing ANN implementation.
Yes. What happened? New learning match. Please open a notebook, the class 22 notebook. Just upload the loan approved data. We'll implement and also we'll discuss few things related to what are activation functions, backpropagation, and optimizers, loss functions today. So from tomorrow onwards, we'll start with a deep learning, which is CNN. And just run the entire notebook. Done running a notebook. So we did all the pre-processing steps like handling missing values, outliers, and also we converted all the text columns into our numerical columns. And also, I guess we're at scalable. Yeah. And finally, we splitted data. Now it's a time to split data for training and testing. Split data for split data for training and testing. Simple. So I'll be using from sklearn bot model underscore selection. Let's just import train test plot. And then it's going to produce four things: extreme, test, y train, y test, which is equal to call your train test plot as your x and y. You need to define a test size, which is 0.2. Random state equals 42. This is how you split data for training and testing. Then once you split your data for training and testing, since it's a classification problem, do we need to apply the smoothing? Do we need to apply a smooth technique to balance our data? First, we'll just plot a graph in order to see how many classes we have. Like, do we have equal proportion or Like, is there a difference in proportion? So PLT dot figure dot fixed size equals 5 comma 2. And then I'll be using SMS dot count plot data comma x equals it's a load status. It's highly imbalanced. So we need to balance it. So for that, we need to implement the smooth technology. Use smooth in order to balance your data. So how do you implement? Simple from IMB learn dot oversampling. You just need to import a smooth. And then we'll be initializing the smooth. So once you initialize, you can also use from collections. You can just import a counter just to see the class distributions. And we know that it should be applied only on a trained data, right? So I'll be calling exampled, comma y sampled equals I'll be calling a smooth dot. So we should use it's a resample or transform. It's a sampling, no? It should be resample. So fit underscore resample. You have to pass your X string comma Y string. Then I'll actually check counter of X string. And then counter of X, sorry. Oh, it should be Y string. Something should be there. So it should be just counter of Y train only. Okay, now let's give it here. Counter of Y train and it should be Y sampled. Yes. Can you say previously it was like highly imbalanced? After applying a smooth, it has become like completely balanced. So it's before balancing. This is after balancing. finish this. Hope it's done. So if done, just give a heading as NLP classifier. NLP classifier. So this MLP in a sense like multi-layer perceptron. Okay? MLP means multi-layer perceptron. So when I say multi-layer perceptron, so from sklearn without neural network, we have to import MLP classifier. You can use the same thing for regression as well if you have a regression data. I'm showing for only classification, so people can try to implement for a regression data. And then you have to initialize your model. The model equals MLP classifier. And then train the model using model.fit extreme or trainer. And then just make the predictions using y-pred equals model.predict. X just one important thing. It's not X train, it should be X sample, comma Y sample, because it's a smooth is applied now. So we are balancing. So that should be taken. That's it. I'll try evaluating your model. So since it's a classification, use classification metrics to evaluate the model and see what is the performance. Done evaluating.
Yes, ma'am.
What is the accuracy?
Ma'am, it's 68%.
Okay. I got 73. Just try rerunning on notebook once. Let me do after doing this. Okay, recall is good. FX score is also good. Great. Okay. All right. So this is without hyperparameters, right? So now let's see with hyperparameters, like what will happen. Any idea what are the hyperparameters of FFP classifier? What are the hyperparameters of a multi-layer perceptron? So basically, you have to define hidden layer size. Hidden layer size is equals. So basically, I want two hidden layers in which each layer should have, the first layer should have 100 neurons and second layer should have 50 neurons. Okay. And then I'll be using an activation function, which is the most popular one, which is a ReLU. And then I'll be using an optimizer. I'll discuss all this today. Optimizer, which is an Adam. And then let's say random state equals 42. And then what else we can give? Okay. Optimizer spelling. Oh, it's not an optimizer, it should be solver. Sorry. Use it as solver. Now try evaluating model using this. Increased or decreased? Decreased. Only recall is improving. Precision, not much. Okay, this is how you deal with hyperparameters in a MLP classifier. Is it clear how to implement machine learning projects? So whenever you take a regression or a classification problems, so these are the different steps, these are the different algorithms that you have to implement in here. All good? Any questions? So take different data sets and just try implementing different things. That's how you explore things. So this is all about AML. Hope it's clear. Done? Okay. I want to discuss few more things related to this AMM, a little bit of theory related to what are the different activation functions we have, different loss functions that we're gonna use, and also the different optimizers, what is back propagation. Let's try understanding all these things. Okay. Yeah. So we'll discuss about different activation functions that we have and its formulas. So we'll discuss about the different loss functions. Then I'll discuss about, what is back propagation. And then different optimizers. Okay, coming to the first one, activation function. So basically, you know that activation functions are basically used in hidden layer as well as the output layer. So what is the role of activation function? Very important interview question. Usually activation functions are used in order to introduce a non-linearity into a data, right? Activation functions are used to introduce non-linearity into a process. So basically, activation functions are used in hidden layer as well as output layer. Very important thing. Used in hidden layer as well in output layer. Yeah. So the very first activation function is basically linear activation function. So just remember in which layer usually it is used, and also what is the range of it, what is the formula, and how does that particular graph look like. So that's like more than sufficient. Okay. So when I say linear activation function, so what would be the formula, range, as well as the graph? How would it like look like? How it will look like? Linear in the sense, right? Linear equation expression, like how does it look like? So just a straight line passing through an origin. So whenever it's a regression problem, usually in that case we use it because it can learn only a linear pattern. It cannot handle a non-linearity. So linear activation function equals it is something like this. Straight line which passes through origin. So the range is going to be minus infinity to plus infinity. It can take any positive values or a negative values. And then the graph looks something like this. And one of the limitation with this linear activation function is like it fails to capture the non-linear pattern. Okay, fails to capture non-linear pattern. To overcome this, we have a concept called as the next important activation function as a ReLU. And also related to this, it is used in output layer, especially when it's a regression problem. Okay, yeah. What is ReLU? Any idea what is ReLU? ReLU in the sense it's a rectified linear unit. Rectified linear unit. You know what happens with our ReLU? So basically what ReLU will do, it basically converts all inputs to a positive. If any negatives found, it will convert into a zero. Most used activation function, which introduces nonlinearity by converting all negative values to a zero and keeping all positive values as it is. Okay, a very important or a most used activation function. In hidden layer, which converts all negatives to zero. All negative inputs to zero and positive inputs remain unchanged. So it has a formula something like this. So it is just maximum of 0, x. For example, let's say your input is x equals 4. Can you tell me what is maximum of 0, 4? And if x is minus 7, so what is maximum of 0, minus 7? Understood? Max of 0, 4. Positive numbers remains unchanged. But when it comes to negative number, what is maximum of 0, minus 7? Isn't it 0? And its graph is going to look something like this. Hope you are getting. So ranges 0 to plus infinity. And the graph is going to be like this. So all the positive values remains the same, but all the negative values becomes a 0. This is a ReLU graph. Hope you guys are clear. Understood? It is just vanishing all the negative numbers to 0. Just vanishing all negative numbers to 0. That's a ReLU. Okay, little advancement towards this ReLU is we have a concept called as a leaky ReLU. So what is leaky ReLU? Just like ReLU only, but ReLU what it is doing, it is converting all negatives to 0. That means we are missing information. So by using leaky ReLU, it allows a small or a non-zero output for negative inputs, instead of making it a zero like ReLU, it allows small values. Okay. I hope this is clear related to ReLU. Next one is third one, leaky ReLU. Even this is one of the activation function. Even this is used in hidden layer. Used in hidden layer. Instead of converting negatives to zero, just like ReLU, instead of converting negative inputs to zero, just like ReLU, it introduces small non-zero values. A small non-zero values for a negative values. So it will have a formula something like this. If it's a positive value, it will be the same, okay? And if it's a negative value, if it's less than zero, so instead of zero, it will be alpha x. So it introduces a small value, small non-zero value. That means we are introducing a small negatives. We are introducing small negatives. Alpha can be a constant like 0.01. Okay. So it is just introducing alpha small constant. Like 0.01, something like that. Okay. I hope this is clear. And range is going to be, since it is including negative values like this, and the graph is going to be like this. So for positive, it will be like this only. For negative, for leaky, it was like this. Because all negatives got converted into a positive. This was a leaky, right? But when it comes to, sorry, this was a ReLU. Now coming to leaky ReLU, since we are adding some constants, alpha multiplied with x, that means we are introducing a small negatives. This is leaky ReLU. So what is happening here? It introduces small negatives and also overcomes dying ReLU problem. You know what is dying ReLU? You know what is dying ReLU? Dying ReLU in the sense your ReLU is making your negative zero, na? If value becomes a zero, your neuron will die. Your neuron will vanish. Understood? Dying ReLU in the sense, since negative becomes zero, in neuron, so neuron dies, vanishes. So that's what we call it, like a dying ReLU concept. This is related to leaky ReLU. Got it? Any questions? We have one more. We call it like a LU. You know what is LU? What is LU? LU in the sense it's an exponential linear unit. So what it does, it's somehow similar to leaky ReLU only. Behaves like a ReLU for positive inputs, but it uses a exponential curve for a negative inputs. Okay, instead of taking alpha x, it will be taking alpha into e power x minus 1. Similar to ReLU only, but it uses exponential curve. Similar to ReLU, for positive inputs, but uses exponential curve for negatives. So it uses a formula something like this. Positive value means it remains the same, x only, same number. If it's a negative number, it will be alpha into e power minus 6 plus or minus. So it's minus 1. So here alpha is a constant. Usually it will be 1. So this is the exponential linear unit activation function. Again, even this is used in a hidden layer only. Okay. Used in hidden layer. How does the graph look like? So basically, LU will have a smooth curve in a negative direction. You don't have a sharp curve, rather you'll have so range is basically it will be alpha and this is plus infinity. Okay, that's a range and the graph is going to be not just an alpha, it's a minus alpha, sorry. Yeah. It takes some small negative values and then graph is going to look something like this. Let's see, this is x for positive values. For negative values, instead of being a sharp line like this, it will be a curve. It creates a curve like this. You get a smoother curve because of this exponential smooth curve. So why is it? So again, even this overcomes the dying ReLU problem. And also vanishing gradient problem. Just remember, I'll discuss what is it in a upcoming section. So vanishing gradient problem. So these two problems, it will overcome. Usually this problem is seen in a tan H and sigmoid, so it overcomes them. Okay. Understood related to LU? Okay. Next one. Tan H. Tan H in the sense like tan hyperbolic. Tan hyperbolic. You might have studied about a tan hyperbolic in your lower classes. So it's an activation function. So what this does, whatever inputs you have, it transforms everything to a range of -1 to +1. That's a range of tan H. And tan H formula is going to be, so you might have studied this in your trigonometry. E power x minus e power -x divided by e power x plus e power -x. This is the formula. Okay. Even this gives you a S-shaped curve wherein it's a zero centered. Okay, it's like just passes through and symmetric around the origin. That's what we call it, like a zero centered. Graph looks something like this. Two boxes. Just a minute. Yeah. So this is the formula, and graph is going to look something like this. See, so this is zero, no? This side like positive x, negative x, positive y, negative y will be there. So the graph goes something like this. It passes through origin. Just looks like a sigmoid only, but passes through origin. Okay. Looks like sigmoid only, but passes through origin. So since it passes through origin, we call it like a zero-centric. Symmetric about origin or symmetric about a zero. Okay, we call it like a zero-centric. So since tan h ranges plus or minus 1. Okay, so basically if you try to find the gradient of a tan h, if you try to find the gradient of tan h, there's a possibility that gradient might become a zero. That's the reason it results in a vanishing gradient problem. If gradient is becoming zero, that means vanishing gradient. Okay, so if you take a gradient of this tan hyperbolic, so gradient of tan hyperbolic is something like this. Tan hyperbolic gradient x equals 1 minus tan hyperbolic square of x. So since this value is tending to plus or minus 1, even if you give a plus 1 to this, minus 1 to this, so this tends to 0. So we call this as a vanishing gradient problem. Okay, if gradient reaches 0 or if gradient of a tan h is 0, we call it like a vanishing gradient problem. Understood? If gradient is 0, it results in vanishing gradient. So this is related to tan h. We'll just take a break for 5 minutes and then I'll continue. Take break till 10:35. You people are back. Okay. So next activation function, we have two more. Oh, we done. I think, okay, tangents. Next one is sigmoid. A sigmoid function already you know. So it's an activation function. Used in output layer, which transforms all values to a range of 0 to 1. You know this, already studied in logistic. Sigmoid formula is going to be 1 plus e power minus z, where that is mx plus. What is the range of sigmoid? 0 to 1. And the graph looks something like this. This is a sigmoid curve. This is a sigmoid curve. Done, clear. Any questions? So this is related to sigmoid. Next one is like we have a softmax. And one more important thing, the sigmoid is used in our output layer, but especially when it's a binary classification problem. Okay. So mostly used in binary classification problem. What if it's a multi-classification problem, multiple labels if you have? In that case, we have one more activation function, which we call it like a softmax. You know what is softmax? So what it does, it just converts all values into a probabilities where sum of all the output should be equal to 1. Okay. Softmax is, you might feel this topic boring, but still these are the interview questions asked related to ANN. Not an implementation. Implementation happens in just 4 lines. I know projects are important, but still along with that fundamentals also important. Because you'll be using activation as a hyperparameter. They can ask which should be used in hidden layer, which should be used in output layer. So softmax is an activation function. Which transforms all inputs to the probabilities, where sum of all probability should be 1. Should be 1. Okay. So its range is 0 to 1, but it adds all probabilities to a 1, and the formula is like this is the formula it will be using. Hope it's clear. It is used in it is used in output layer. It is used for multi-classification problem. So this is related to activation functions. I hope you got it. So two things. So what all used in hidden layer? What all used in a output layer? So ReLU, leaky ReLU, LU, tanh. Used in hidden. Sigmoid, linear, softmax. We know sigmoid basically for binary, softmax for multi-class. Got it? Understood? Cleared about our activation functions? And also we discussed about our two things. One is dying ReLU problem. It's because of converting all negatives to 0. Neuron becomes dead. And also I discussed about a vanishing gradient problem. Usually appears in tanh and sigmoid. Vanishing gradient in the sense the gradients will tend to become a 0. Gradients will vanish. Okay. Yeah. So this is all about the activation function. Next important thing. So we have learned about the forward propagation, wherein the learning happens from input layer to hidden layer, from hidden layer to output layer, wherein output layer is responsible for making predictions. So basically, once predictions happens, how do you know how good is your model? Don't you think we have to use a concept called as a loss functions? So now it's important to understand what are the different loss functions used in our regression as well as a classification. Loss function in the sense, it's an error function used to find overall mistakes done by model, right? So when I say loss function, again, you have two different things. So one is regression. What are the loss functions associated with the regression and what are the loss functions associated with the classification? So can you tell me what are the loss functions used in regression case? Loss functions used in regression. So already studied mean squared error, mean absolute error, root mean squared. It uses mean squared error. When I say mean squared error, and then we have root mean squared error, which is RMSE, which is square root of MSE. So these are the loss functions used in ANN whenever it's a regression problem. So similarly, we have a loss function for a classification. In that we have two things. For classification, we have two things. For binary classification, which loss function we use, and for multi-classification, which loss function we use. Any idea? Loss functions associated with classification? So when it's a binary classification problem, we use a concept called as a binary cross entropy, which is also called as a log loss. Binary classification in the sense like two classes will be there. So how will be the formula? So it will be minus y times log y plus 1 minus y into log of 1 minus y. So y is an error made by the positive class, 1 minus y is a error from a negative class, something like that. Clear, understood. This is for a binary cross entropy, wherein we will be using it with a binary classification problem. So when it's a multi-classification problem, any idea which was the loss function used in multi-classification thing? It's a categorical cross entropy. If there are multi-classes, so categorical cross entropy. So it is used in multi-classification problem. Okay, and the formula is going to be loss equals so there will be multiple classes now. So it will be using something like summation by log pi minus summation by log pi. Pi, yeah. So this is the loss function it will be using. This is all related to activation functions and loss functions. So now, once you find a loss, let's say, for example, in your forward propagation, the prediction has happened. You have found loss using these formulas. Now you will understand that, okay, loss is high. So now what to do? So what we have to do? So data is fixed. I cannot change the data because it's already available. So what can be changed when it comes to an artificial neural network? What did we add extra when it comes to a neural network? Do you remember W and B? Yeah. So when I see back propagation, if loss is high, we have to focus on updating weights and a bias in a reverse direction. Okay, we call that process as a back propagation. So back propagation is all about, updating weights and bias so that error is minimum. So since we go in opposite direction, updating everything, we update all the weights, biases, updating all the activation functions. So that's the reason updating, going backward in the sense we will be finding the gradients. So you have two concepts. One is a back propagation, and that could be achieved with the help of optimizers. I want you people to explore on these two. I'll discuss tomorrow first this particular thing, and then we'll start with a CNN. And from next week, I'll show two deep learning projects, images related project, and then we'll start with NLP. After I finish NLP, I'll show the deployment. Then we'll start with a generative AI. Okay. Clear? Any questions, guys? So all these things, whatever I discussed, different layers in neural network, forward propagation, what is perceptron, what is activation function, what are weights, biases, different loss functions. Next thing I'll be discussing about a back propagation, like how the process is going to work. People can ask you, explain back propagation. Optimizers, you have a different optimizers in that I'll be showing a gradient descent. So all these things are like super important. Most frequently asked interview questions. Okay, all good?
Guys, tomorrow there will be class, 9 o'clock.
Yeah, tomorrow you have a class. This is the first batch, not today. Yeah, you have at 9 o'clock, 9 to 10:30 will be your batch. Just for tomorrow.
Okay, you can submit your task on Sunday.
Okay, thank you. So make sure you record a video as well. And I could see many of the people doing a project not writing insights for the graphs. If you are not writing insights, like what you are understanding, insights, documenting, comparing models, doing hyperparameter tuning, everything is important. Whatever I'm showing in detail in class, everything should be in your project. Okay, don't do for the sake of us, do for you. It should be like complete end to end with a proper clean structure, not just randomly doing a project. Okay, all right, thank you. We'll catch up tomorrow.